Hello friends. So in this video we will learn to find the shortest path in the graph. In the previous video we have seen that the Shikshra is the most popular algorithm to find out the shortest path. But the limitations of the Shikshra is that it is not working on the graphs which have negative weight edges. So to find the shortest path with this kind of graph, the Bellman-Ford algorithm is most popularly used. So we'll see how to use this Bellman-Ford to find the shortest path. So Bellman-Ford algorithm is used to find a single source shortest path that gives the shortest path from one source to all other vertices, even if the negative weight edge is present in the graph. Also, it tells us that the graph contains any negative cycle or not. So what is the meaning of negative cycle? Negative cycle means if there is any cycle present in the graph. Example, this is a kind of cycle where you are moving from one vertices to another and you keep on moving in the same path. So if you add all the weights of these edges, for example minus 6 plus 3 plus 2, and we are getting here minus 1. So if the weight of this cycle comes out to be negative, then it is said to be a negative cycle. So we can see here this is one graph given to us and we need to find out that negative cycle is present in this graph or not. So you can see that let us suppose this is a directed graph and we are making one cycle in this graph. So this is a kind of graph where you can see this is this path B, C, D, B, C, D, B. This is a kind of cycle present here. And if we add all the edges in this cycle, you can get 1 plus minus 4 plus 2, that is equals to minus 1. So again, this is a negative value coming, then that is means a negative cycle is there. So negative cycle means that we will not be able to find a shortest path from any source to that particular vertex. If the cycle is positive, then there is no problem. Means, for example, if in place of this minus 4, if it is 4, then we will be getting for the cycle 1 plus 4 plus 2, that is equal to 7, and which is a positive value, and it will create no problem. Why? Because in the Bellman-Ford algorithm, we are using the concept of relaxation. So while relaxation, we keep on improving the distance value. So if there is any cycle is present, it's keep on increasing the value. That means we will skip the cycle. Automatically, the cycle will be skipped because each cycle will be definitely increasing the d values. But if the cycle weight is negative, then each cycle will keep on decreasing. And because we are working on the concept of relaxation, it will keep on decreasing at each iteration. That's why if the negative cycle is present in the graph, then there is no path possible. So we will see what is relaxation, and then we will apply the Bellman-Ford algorithm to find the shortest path in the graph. So this is Bellman-Ford algorithm, and if we look at this algorithm, we need to initialize first, and for initialization we are passing the graph and one source. So in this initialization process, we are assigning the d value of s equals to 0 and the d value of all other vertex equals to infinite, and then we are putting one for loop is will be for these three statements, and this for loop will work for vg minus 1. That means if in the graph we have 6 vertex, then we are doing some operation 5 number of times. Now what actually we are doing, we are doing v minus 1 times relaxation, and then when we come out of this loop again we are doing a kind of relaxation, and if you are able to apply the relaxation, the answer is false, otherwise it is true. That means even after doing v minus 1 time, if you are still possible, means after the v minus 1 time means at the vth time, if we are still possible to relax any of the vertex, that means the negative weight cycle is present there, and the path is not possible. So point to note there that if n vertices are there in the graph, then we need to do n minus 1 times relaxation, and after reaching n minus 1 time, then we will do one more time relaxation to check that there is a negative cycle or not in the graph. So we'll take one example and we'll try to understand this. So let us take this example and we will apply this algorithm to find the shortest path. So here you can see we have 4 vertices are there. So 4 vertices we are having, that means we need to do 3 iterations. So maximum of iterations will be 3. Now one thing we need to understand, this is the maximum iteration that is required. It doesn't mean that every time we need to do v minus 1 iteration. There may be a possibility that if you have let's say 6 vertices, then you may get the answer in 2 iteration or 3 iterations or 4 iteration or 5 iteration, means the maximum iteration required will be 5, but there is a possibility that you may get the answers in the second iteration or third or fourth iteration. And one more thing, it is given in the algorithm that if you are reaching to the v minus 1 iteration, we are assuming that we have 6 vertex, that means the maximum iteration that we are doing is 5, and if we are doing up to the 5th iteration, then only the 6th iteration is required to check for the cycle, otherwise it is not required. Again I repeat, the meaning of this is, let's say we have 6 vertices, that means we need to do 5 iterations, but if you are getting your answer in the second iteration or third iteration, then there is no need to check for the negative cycle. Negative cycle is only present when you are reaching to v minus 1 iteration. Now what does it mean? It means when I say that you may get the answer in second iteration or third iteration, what actually we are doing, we are finding the d value at each iteration. We are finding the d value at each iteration by doing the relaxation, and when we find the d values at the second iteration, and when we are doing a third iteration and we find that none of the d values are going to change, d values of the vertex are not changing in the next iteration, that means you got the answer. If it is changing, that means still there is a possibility to improve the path, and we will be keep on doing up to the v minus 1 times. So let us take this example and we will. So let us see this example. We have 4 vertices, so we are need to do 3 iteration. So before we proceed, we need to write some information. We will write the information about the edges and their weights. So now one thing to understand is, as in the Dishiktra, if you remember, when we start this procedure, we have to start from the source. But here we have a defined source, but we are free to start from anywhere. Let's say the source in our problem is 0 and we are interested to find the path from 0 to all other vertex, but we can start from anywhere. So let's say I write here I'm writing the edges and their weight. So edges I am having 1 2 3, means what, this is one edge is there and the weight is 3. Then I have 3 to 2 and the edge weight is 2. Then I have 2 to 1 and this is minus 6. I have 0 to 2, which is 4. Sorry, this is not minus 4, this is 4. So let me do the correction. 0 to 2 is 4, and also we have 0 to 1, which is 5. So I have 1 2 3 4 5. We have 5 edges in our graph. Let me again write it like this, 5. Okay, so now we have the edges and the weight. Now I am going to write the d values of each vertex. So here I am writing d values of the vertex. So we have vertex 0 1 2 and 3. And one thing you need to remember here, that I have written here 1 3 weight is 3, 3 2 weight is 2. You can start from any edges. There is no, I mean, there is no compulsion to start from one, means from this path. You are free to start with any edge. So here I write the means this dv values. So initially we are doing the initialization process, and that initialization process we will be assigning the source to be 0 and all other to be infinite. And now we will apply the relaxation process. So this is iteration number 1 we are going to start. So we have to read all the edges and find the change in the dv values. So here, and if you know that dv, if dv is more than du plus uv, then only we need to check, means we need to change dv equals to du plus uv, and also we will change the parent of v to u if this is the situation is uh, applicable. So here, now this is u and this is v. When I say u and v, this is the vertex from where you start and v is the vertex where you are reaching. So 1 2 3, this is u and this is v. The du value here is 0. Sorry, for 1 you can see this is infinite, and this is also infinite. So if you add, if you put the values here, so du is what, infinite, and uv is 3, and dv is also, means v is what, 3 here. So the d value of 3 is infinite. So here you can see that infinite is not, is more than infinite, so we are not going to change this. So we are not able to change any d values in 3, so we will just skip this and we move to 3 and 2. Now here, the d value of 3 is infinite, the d value of 2 is also infinite, and we are not able to improve this d values. We can move here. So if you find it difficult to understand, just hold on for 2-3 minutes, you will be able to understand how I am doing these tables. Now 2 to 1, 2 is infinite, 1 is infinite, we are not going to change anything because both are infinite. Now look here, 0, the d value of 0 is 0. So if you see, I am using this formula here. So u and v, so this is u here and this is v. So the dv value of, means the d value of 2, d value of 2 is infinite, and d value of 0 is 0, and the edge u to b is 4. So you can see here that infinite is more than 0 plus 4, means here this condition is actually holds. Whenever this condition hold, then we will put the d value equals to this. That means now we are going to make the d value of 2 equals to 4, means in place of infinite I am changing it to 4. And how you are getting this 4 value? Because of 0, because when you remove from 0 to 2 you get this 4. So also I am writing its parent, predecessor, so I am writing here down. That means that the new d value of 2 is 4, and I got this d value because of 0, means from 0 I am getting this d value. Now 0 to 1, 0 is what, the d value of 0 is 0, and the d value of 1 is infinite, and the edge weight is 5. So this is again a kind of this situation, infinite, and this is 0 plus 5, which is infinite is more than this value, so we are going to change it. So here you can see that 1 is going to replace with 5, and this is happening because of 0. Now you see here we have read all the edges, and you can see that in this iteration we have changed some values, we have find some values. If these values, if this iteration means this is blank, if all are blank, that means we are not able to improve this and we got the answer. But because we have some entries here, we need to move to the next iteration. So iteration number 2 we are doing. Again we will be reading all the edges. So before we start, let me clean this area. Okay, so now we can do the next iteration. In the next iteration, again we need to read all the edges and change the d values. So 1 2 3. So you can see the d value at 1 is what, the d value at 1 is 5. So when I say 1 3, 1 3 is actually, when I say 1 2 3, this is actually uv, u to v. Okay, so now I am using this edge and I am applying here. So the d value of 3 is what, now this is v here. The d value of 3 is what, infinite, and the d value of u, now u is what, 1 here. So the d value of u is 5, and what is the weight uv, that is 3. So you can see here that this is infinite and this is 8, and this infinite is more than 8, then we are going to change the d value. So here you can see that in the second iteration we are going to change the d value of 3, which is going to be 8, and we are getting this 8 because of 1, so I'll write this is 1 here. Similarly, I can do for all the edges, and I hope that now you understood how I am doing. So 3 to 2. So you can see the d value of 2 is what? 4. Now we will always use the updated one. This is now no more existing. So this is 4, and the d value of this is 3. So you can simply directly do it. How can you do this? You can go to 3. This is 3 is 8. 8 plus 2 is 10, and you compare this 10 with the d value of 2. So d value of 2 is 4. So 4 is actually less than 10, so we are not going to change anything. Now 2 is what? 2 is 4, and 4 minus 6 is what? 4 minus 6 is minus 2, and this is 5. So minus 2 is actually less than 5, so I am going to change this d value. I will write here minus 2, and this I am getting because of 2. Now 0 2, 0 is 0, and this is 4, and 2 is what? 2 is 4. So this 4 is not less than 4, so we will not do anything. We will only change when we are going to improve. Improve means if you are going to lessen the d value, then only we can change it. Now 0 to 1, 0 is 0, and 5, 0 plus 5 is 5, and 1 is what? 1 is minus 2. So minus 2 is already less than 5, so we are not going to change anything. So because we see some values here, that means still we need to move to the next iteration, 3. If there is no values occurring here, if this is all blank, that means we got our answer. So we are going to the third iteration. Again we do the entire process. So I start from 1 to 3. So 1, the d value of 1 is minus 2. Minus 2 plus 3 is 1, and 3 is what? 3 is 8, so I am going to change, this will be 1. Again I repeat, the d value of 1 is what? This is minus 2. So minus 2 plus 3, and this side the d value of 3 is what? 8. So 8 is more than 1. So that definitely we need to change this. So I am going to change this to 1, and this I am getting because of 1 to 3. So I am writing here 1 because I am reaching this, because I am getting the value because of this vertex 1. Now 3 to 2, the d value of 3 is 1. Now this is 1, now not 8. So this is 1. 1 plus 2 is 3, and the d value of 2 is 4. So I am going to update is to 3, and this I am getting because of third vertex. Now 2 to 1, the d value of 2 is 3, and 3 minus 6 is minus 3, and at 1 we have minus 2, so minus 3 is less than minus 2, so I am writing this, and this I am getting because of 2. Now 0 to 2, 0 is 0, 0 plus 4, 4, and 2 is 3. So I am not going to change the value because 4 is not less than 3. Now 0, 0 here is 0 and 5. So if I write using this formula, then the d value of 0 is 0. I am writing this side, and the distance is 5, and v value, that is 1. The d value of 1 is minus 3. So minus 3 is actually, this condition does not hold. So we are not going to change anything because minus 3 is already less than 5. Now because we are reaching to the third iteration, and in the graph we have 4 vertex, that means we must got this answer in the third iteration, because it is given in the algorithm we need to do only v minus 1 iteration, where v is the number of vertex. So here we have 4 vertex, so we need to do only third iteration, and since we are reaching to the third iteration, we need to check the fourth iteration also. Now what does it mean? Now we will apply the same procedure for the time, and we see that the values in here. Now if we are going to get the same values like the third column, that means we got our optimal answer and there is no cycle present. But if you got values in the fourth column which is not same as the third, that means the cycle is present and we did not find the shortest path in this graph because of the presence of negative weight cycle. So we'll check the fourth iteration. So before we start, let me clean this area. So now we do the fourth iteration. Again, we start from the this edge 1 to 3. So again, I am using this 1 to 3 means this is u and this is v. So I will write, I will just using this formula. So d value of 1 is what? D value of 1 is minus 3, and this is uv is what? 3. And what is the value of, and this is right hand side, this is dv, means this is v here. So the d value of 3 is 1. So you can see here that 1 is more than 0, means this condition is hold. So we will be updating this d value. Whenever this condition is true, we will update this d value. So now this d value of 3 will be changed to 0, and this we are getting because of this u, that is 1 here. Now again we will apply the same procedure, 3 to 2. So I am using this right hand side. So d value of 3 is 0 plus uv is 2, and d value of v is, that is d value of 2 here is 3. So you can see that 3 is more than 2. So I am going to replace this 3 with 2, and this I am getting because of 3. Now 2 to 1. So 2 is what? 2 is 2, and minus 6. 2 plus minus 6 is minus 4, and 1 is minus 3. That means again we will going to change this minus 4, and this is because of 2. So actually there is no need to solve all the values. We can observe here that the values are, means not same as in the as in the third, means column, third iteration. That means there is a negative cycle present in the graph and we are not able to find the shortest path here. And this tells us, this fourth iteration will tell us the presence of negative cycle. If for assumption, means in this case we have a negative cycle, and you can see here in the graph, if you take this part, this is a cycle, and if you add this minus 6 plus 3 plus 2, you can see this is minus 1, which is a negative cycle in the graph. Let us understand one more thing. Let's say you are reaching up to the third iteration, and we need to do the fourth iteration as well, because we are reaching up to v minus 1 iteration. And in the fourth iteration, if you are getting something like this minus 3 3 1, which is same as the third iteration, that means this is our optimal solution, this is our final solution, and there is no negative cycle present. And one more thing, let's say this is the situation, that means how can we conclude the answer? That means from 0 to 1, means from the source 0 to 1, the cost is minus 3, and you can reach with the vertex through the vertex 2. From 0 to 2, the cost is 3, and you can reach to the vertex 3. From 0 to 3, the cost is 1, and you can reach to the vertex whatever is written here. So this tells you the cost, and this tells you the vertex, the parent from where you are reaching to this. So hope you have understood the Bellman algorithm and how to apply the algorithm to find the shortest single source shortest path in the graph which have negative weight, and also we can find the presence of negative cycles. So see you in the next lecture. Thank you.